I want to say a few words about the importance of temperature in geomorphology. We've already identified that geomorphology involves energy acting on materials to drive processes, and that those processes create landforms and landscapes. But that interaction between the energy and the materials depends to some extent on environmental controls of different types, and temperature is a good example of how those work. So we'll look at that in a little bit of detail in this session. We can approach this topic by going right back to the beginning and thinking about some of the big questions that lie at the heart of geomorphology. People sometimes think that geomorphology has to be about really difficult, tricky, intricate, detailed questions. It doesn't. Often the big questions are the useful ones and the interesting ones to at least get started with. So at the biggest level, you can look at a landscape around you. You could look out of your window or go for a walk around your garden or your local area and just ask the most basic questions. Why are there hills? Why is this bit flat? Why is this bit at such and such a gradient? So in these images, there are hills of different types. Why are they there? Well, they're there because of processes which are operating on those landscapes. Processes such as uplift, erosion, transport of sediment and deposition of sediment. Some hills are erosional remnants, other hills are created by tectonic processes, but it's these processes that are driving the creation of the landforms. So if landforms are created by processes, what is it that controls the operation of these processes? What's determining the rate that this material is moving down this slope? What's controlling the rate at which this river is eroding the valley? What controls the way the glacier is affecting the surface of this volcano? What controls the operation of the volcano? What controls the movement of sediment down the side of the volcano? There are all sorts of different processes going on. What's controlling those? We've already looked at things such as stress versus strength, applied force versus resistance, gravity versus friction. We talked about that in the previous session. But the other thing we started talking about was the characteristics of the different materials that are involved. So soil behaves differently from water, which behaves differently from ice, which behaves differently from wind when it impacts on a sandy hill slope or whatever. So not only the driving and resisting forces, but the characteristics of the materials are also really important. And a lot of materials, their characters vary depending on their environmental setting. So here we've got some water flowing through a cold environment and the water is freezing and turning to ice. And as we change the temperature, the characteristics of that material change. Here we have volcanic eruption. As the temperature of the rock changes, it can go from being a fluid state into a solid state. So environmental factors control the properties of the materials that we're dealing with in our geomorphological situations. One example of these environmental factors is temperature. And in these situations, you can see that temperature controls, first of all, the phase of the material. Is it in a liquid phase? Is it in a solid phase? It controls the viscosity. Warmer materials generally are more fluid, less viscous than colder materials. The density of the material, the hardness of the material, all sorts of different characteristics of the material are being determined here by changes in temperature. So we're beginning with some very fundamental geomorphological questions that are leading us towards this topic of temperature. Why is the landscape like this in this particular location? What environmental factors are controlling the processes going on here? Why is it that this location is different from another location? Why do landforms and processes vary from place to place? And how do the materials involved behave differently in these different environmental settings? Those are very fundamental questions about geomorphic controls on landscape development. And you can start asking these questions about your own case study landscapes, your own favourite landscapes, your own local landscapes. So let's have a look at a little case study, temperature in geomorphology. And the key points that I want to make here is that temperature does make a difference. I've stuck just for a bit of fun, I've stuck a slide in here of one of my field assistants from a trip to Greenland many years ago, who was a little bit surprised when the temperature at -30 turned out to be pretty chilly. your toothpaste froze, and all sorts of different things happened at that temperature from what we're used to at our normal day-to-day temperatures where we're based in Kiel. So changing the temperature from a very cold environment to a very warm environment, even within that fairly narrow range, very obviously in a common sense way, makes a difference to us. Well, that's true for geomorphology as well, not just for our comfort levels. Temperature is important in a variety of different ways, but in particular, this is one that I want you to think about when you're wandering around and looking at things in your own local environments. Temperature is important because of the temperature dependence of the physical and chemical properties of materials. In other words, if you change the temperature, the physical properties of a material are going to change, and in some situations its chemical properties, or certainly the rates of chemical reactions, will also change depending on temperature. So going back to our example of ice and water, changes in temperature above and below the freezing point cause changes in the structure of the material, the atomic structure of the material. Those changes in structure lead to changes in the properties of the material, liquid versus solid. And those changes in properties lead to different effects. If we were meeting in person in the lecture room, I'd have a bucket of water and I'd have a bucket of ice cubes. I'd throw the bucket of water over one side of the class and I'd chuck the bucket of ice cubes over the other side of the class, and those two buckets would have different impacts simply because of the temperature of the material in the bucket, which leads to different structures, which leads to different properties, and thereby different effects, partly in terms of consequences of students suing me for getting them wet or banging them on the head with ice cubes. In a geomorphological context, we've already seen examples of how this works in our previous sessions. So for example, we've talked about how glaciers move by creep as a result of the relationship between stress and strain. The amount of deformation in ice is a function of the stress applied to the ice multiplied by a factor for the hardness of the ice, and the hardness of ice is dependent on temperature in the same way that the viscosity of most materials is dependent on temperature. So we have the stress related to the strain through this medium of viscosity or hardness, which is temperature dependent. Likewise, when we think about a glacier sliding across the bed, the friction at the bed is controlled, amongst other things, by the presence or absence of water. If you try to slide across a wet bed, it's very much easier with that lubrication than trying to slide across a dry bed. The presence or absence of water underneath the glacier is temperature dependent. So this PW, the water pressure term, is very much a temperature dependent term in the movement of glaciers. And as you think through all sorts of different geomorphological examples, hopefully you'll be able to think up, and in your independent reading you'll be able to find out about all sorts of different little ways in which temperature controls the characteristics of materials. Water's a good one to start with, and that difference in characteristics of the material leads to changes in the nature and the rate and the effectiveness of the geomorphic process. And that applies in lots of different geomorphic situations. Here's another really obvious one, a volcanic setting, where at this temperature that rock is mobile and flows, has a certain viscosity. As we cool it down, as we allow it to cool, the viscosity increases until the rock solidifies and sets, and landforms are created based on that change of temperature from a previously flowing state to a now set and solidified state, in this case on the right, retaining some of the flow characteristics that were generated during the mobile state, but are then preserved in the solidified state later on for us to interpret or read that landform to figure out the fact it was indeed caused by the flow of the material of which it's made. So you can find examples of this temperature impact in lots of different geomorphic settings. I'm just going to go slowly on this slide and let you have a little look and a think about where temperature is important in each of these different pictures. I'll just give you a few seconds to have a little think about the role of temperature in these four different images. What about this one in the top left-hand side, there's obviously a very different temperature regime going on in the foreground from in the background, related presumably to the altitude of those mountains. You can see the snow up there telling us about the colder environment, and so you can imagine different types of processes going on in those different settings based on altitude, leading to a difference in local climate, leading to differences in temperature. Temperature in different parts of the world affecting things like soil moisture and the ability of different plants to survive in different environments. So there are links between temperature and biogeography. In the bottom right here, we've got some frost-shattered rocks in Iceland, a very direct impact of temperature fluctuations on the properties of materials, leading to frost shattering or to thermal shattering as the rock or water within the rock or within cracks in the rock expands and contracts. And this one of a rusty roof on a shed, I just put that one up there to encourage you to think about the fact that chemical reactions, the rusting of this roof is essentially a chemical weathering process. It affects the tin roof and it would affect rocks similarly. This oxidation process and most chemical processes are temperature dependent. Most chemical reactions work better in warmer conditions. Some work better in colder conditions, but they're the exception. For the most part, in warmer and more moist conditions, chemical processes work better, so weathering is more effective. So weathering, one of the major processes affecting geomorphic systems, is a temperature-dependent set of mechanisms. Again, here you can take your own time afterwards to have a think about these different images, but temperature at a global scale leading to distribution of earthquakes and volcanoes, and then thinking down to a more local scale what's happening in that particular volcanic case study, and the glaciers on top of it, what's temperature dependent in there, about where's the ice, where's the water, what's the volcano doing, and then looking even closer, here's the bed of a former glacier, and by looking at the very small scale features left behind by that glacier as it slid across the bedrock here, we can infer something, we can work something out about the temperature of the glacier, because glaciers with warm bases tend to slide more and be more erosionally effective than glaciers with cold bases. So here we're working out that this is the bed of a former warm-based glacier. So this microgeomorphology is again thermally controlled, related to the temperature at the base of the glacier that created these landforms in the past. And back to the grand global scale again, here's a raised beach on the west coast of Scotland related to long-term climate change, long-term sea level change, the formation and the subsequent melting of ice sheets, raising the sea level eustatically and isostatically. There's a temperature component in there to the rise and fall of sea level and to the comings and goings of glaciers, and that's now being reflected in these indirectly in these raised beach coastal landforms. So there are lots of different landscapes that you can look at, and either in an immediate context or in a broader scale you can identify the impact of temperature on the landforms or on the processes that have created those landforms or on the properties of the materials that have been involved in the creation of the landforms. So you can look at the landscape and pull out this temperature control. Try doing that in your own back garden, in your own chosen case study for the module. I'm going to move quite quickly through this topic, but you can give it some thought afterwards if you wish. Just give some thought to what controls the temperatures in geomorphic systems. There's a geography to this. The energy available to geomorphic processes isn't the same anywhere. The major inputs are solar energy, and that controls some of the big parts of the system such as climate, and also energy from the Earth's interior driving, for example, plate tectonics and volcanic processes. There's also energy being driven by or being provided by the processes themselves, for example kinetic energy, movement energy, for example the frictional heating. Even sliding a glacier over its bed generates friction, which generates heat, which can lead to melting of the base of the ice. So there's a variety of different sources of energy that we need to think about. And if you think that processes related to energy are partly climate controlled, that's a perfectly reasonable way to think about it. But what controls climate? Why is it that the climate here in Greenland is different from the climate here in Spain, for example? And there are all sorts of different controls that you can identify that are influencing that. The latitude, how far you are from the equator, how close you are to the poles. Altitude, how far above sea level you are. What the local cloud cover, air cover. All these different factors are influencing what the local weather and climate are in a particular area. So if you're trying to predict what kind of geomorphic processes will be going on in some particular spot, well, then you'd need to take all these kinds of factors into account in order to predict what the local meteorological climatic temperature is likely to be. And remember, of course, it isn't simply the temperature or the average temperature that matters. It's other characteristics of the temperature regime. For example, in a periglacial or permafrost environment, yes, we're interested in the fact that temperatures are low, but we're also interested in the fact that temperatures fluctuate above and below the freezing point. If temperatures are permanently low, well below freezing, we get a very different range of processes happening from the situation where temperatures are low for part of the time, but warmer for part of the time. Cryofraction, frost shattering, phenomena associated with the development of an active layer, the segregation of ground ice, lots of the things that either already or in the future you will learn are associated with periglacial and permafrost environments. A lot of them depend on that fluctuation above and below the freezing point, not just on the cold temperatures. And these different impacts can interact in quite a complex way. For example, if you think about at any location, slopes which are facing towards the equator and slopes which are facing away from the equator, so slopes with different aspect, all sorts of different things are going to be happening on those slopes. I'll try and show you a little bit more about this in a later session. So different aspects can lead to different amounts of incoming solar radiation. That's going to lead immediately to direct variations in temperatures, in the range of temperatures, and in the variability of temperature on either side of that slope. Those temperature changes are going to lead to difference in moisture availability. There'll also be differences in whether the slope is more or less sheltered from the prevailing wind. Moisture availability, temperature, and wind, that's going to affect, for example, the duration of snow cover. It's also going to affect the vegetation growing on either side of those slopes. The changes in vegetation, the duration of snow cover, well, that's going to affect the development of soils and vegetations. That's going to affect how much moisture is lost from the surface. So surface moisture, vegetation, that's going to affect surface runoff. How much rain falls on the slope? Well, how much of that is caught by the vegetation? How much is caught in soil? How much is melting off from snow each year? Well, the amount of surface runoff that we're getting, that's going to affect erosion on one side of the hill slope versus the other side of the hill slope. So we'll get different slope profiles. I'll come back to this later on in the module and talk about how this works. But just be aware that once you make one change in a geomorphic system, there are going to be lots of knock-on effects from that, and you can trace impacts on landforms, landscapes and processes quite a way down your process hierarchy, if you like. There are lots of implications of any difference that you can identify. For now, I'll just put in this little example of an asymmetrical slope system. So we have a valley here with, well, you have a sunny side of the slope there, you have a shady side of the slope there. Those differences in aspect are one of the things which are contributing to different processes, different things happening on different sides of the slope. Bear in mind, of course, there are also anthropogenic implications in that people will do things. Farmers will grow different things on different sides of slopes, and that will affect the processes that are going on. But as I said before, the amount of time that moisture stays on a hill slope, therefore the type and amount of vegetation that grows, therefore the nature of the runoff down the valley side into the stream at the bottom, are all going to be different. I'll say more about this in a different session, but for now, just think about what you can pick up from the landscape that is indirectly temperature related. Always try to read the landscape and look for all the different controlling factors that we're talking about somewhere in what you're seeing in the landforms. If you'd like a slightly more exotic example, here's an old paper talking about geomorphology on Mars. I'll stick a more recent example of that, or you can find more recent examples of your own in the literature. I'll put an example on the KLE for you. But there are lots of examples not only on Earth, but outside of Earth, where temperature effects are having a major impact, or have had a major impact, on geomorphic processes and landform creation on other planets as well as Earth. So that was a fairly quick run through, and I'll add some more resources onto the KLE that will help you to develop the ideas in here. But what have we said? We've said that temperature matters partly because temperature itself drives processes, but also it matters because it controls the properties of materials that are being affected by those processes. Temperature is controlled by other things, so we can slot it into a big hierarchy of how our geomorphic system is working. There are factors that control temperature. Temperature then is a factor that controls other things. The available energy that's controlling temperature, and therefore the temperature distributions themselves, are geographical in nature. So one of the reasons that there are so many different types of landform, process and landscape around the world is because of this geography of energy availability, the geography of temperature, the geography of different material types related, for example, to geology, and all those different geographies are interacting to give us the geography of geomorphology, which is, well, what this module is called, the regional land systems. They are the regional land systems, the land